In this video, we are going to study a parallel algorithm for the hybrid-BSP model. An example of a hierarchical machine with both distributed memory and shared memory is the Fugaku supercomputer in Japan. On the top, you see the hierarchy. On the left, there is a single CPU. On the right, there is a rack. And in between, the CPUs are organized. The CPUs are nodes. They're organized in bigger and bigger chunks. The biggest chunk is really a complete rack. On the other hand, a single node does have multiple cores, and these we will consider as the processors. And for example, in this case, we have 48 compute cores in a single node, and you see the detail at the bottom left. So if we want to model this, we really need to make a distinction between the shared and the distributed memory. We want to reflect the hierarchy of the actual computer. Here we see that we have two nodes, each with 4 cores, and each node is itself a BSP computer, and they are also connected as a BSP computer by a communication network, though the network within the node has lower values of G and L than the network of the whole machine. The bottom level we call level 1, the top level is level 2, and the parameters that belong to it are G1, L1, and also G2, L2. Now a question to you: what would be the main benefit of this model? Okay, as you may have guessed, communication within a node is a lot cheaper. So if you can design your algorithms to take that into account, then you have enhanced locality within a node, and hence communication is faster, and actually also synchronization. Still, having 2 levels doesn't complicate too much, because we still like the simplicity of the BSP model, and in this way we maintain that. So we only use 2 levels, and that will get us a lot farther. And this is what an algorithm would look like for the hybrid-BSP model. We have supersteps within a node. You see communication between the cores of a node. On both sides you see algorithms running. And at some point there is a global synchronization between the nodes, meaning between all the cores. And there's also then a global communication where the nodes interchange data. So now that we know what the architecture and the algorithm is, we also need a cost model. We again use the H relation, but now we're talking about nodes and cores. If we're talking about processor P, then S is the number of the node, and T is the number of the core within that node. So that's just a numbering. It looks like a 2-dimensional numbering. Then the cost of a global communication superstep is an H relation. So it is, the global cost is H times G2 plus L2. We have the subscript 2 because we're talking about level 2. And then the question is, what is H really in this case? Well, it's the total, it's the maximum number of data words that a node sends to another node. Now, what is then the cost of a global computation superstep? Here we have to take into account that every node runs a BSP algorithm. So there we get an ABC formula, AS plus BS times G plus CS times L, and the G and the L are then G1 and L1. if we take the maximum over all of those, then we get the cost, and we have a global synchronization at cost L2 that we add to that. So that's the cost. You see, it becomes already more complicated, and it may be easier if it happens to be that all processors, all nodes, run the same internal BSP algorithm. Then the analysis becomes somewhat simpler. Okay, now we're going to look at the sparse matrix vector multiplication. So we have our nodes, and we're going to discuss the fan-out. The fan-in will be similar, so we won't do the whole algorithm, but we will have a closer look at the fan-out. Now, every vector element Vj is stored at a processor, and that's the processor phi v of j. That's the source. And then first we get this data from, if you need it in a node, then first the node gets it in a global communication supersteps. So it gets it from the source, and then it stores it at one designated core of the node, and that core is numbered phi v with a superscript s of j. So it's the owner of the local copy. You only do this if you need it. And then if we have locally stored on a core a non-zero aij, then we have a function phi ij where the first where component 0, phi 0 of ij denotes the node in which it is stored, and the component phi 1 of ij denotes the core in which it is stored. And having done all of this, we can write down our algorithm. Note that it is an algorithm for processor PST, so it is node S, core T in that node. The first two supersteps, they are a global fanout and a local fanout. So in the global fanout, you first, if you are the designated core, then you get the Vj from its source. And after that, for all the j's for which your matrix column is non-empty, and that's expressed by this set j of st, for all the columns that are not empty locally, you need Vj, so you get it. And where do you get it? From your local designated owner. So that is a local superstep, it's a local fanout. And then we have all the information we need to perform the local sparse matrix vector multiplication. It looks like what we've seen before in just the plain, the flat BSP model. So for all the rows that are not empty locally, we add aij vj to a local partial sum. And that's my contribution as a core to row ui. And since I am processor st, core st, then we call this u of ist. So we have a triple index. Now that we have our algorithm, we also want to partition the data to get as little communication as possible and still have a good load balance. We do that by using the Mondrian. And the way to do it is first to split it, to partition the matrix for the nodes, and then partition within the nodes. So for this first partitioning, we need a suitable load imbalance parameter, epsilon 2, which is less than the epsilon that we need overall. And then when we split again, we have for every node S, we have an epsilon 1s that we need to do to get to the final result. Okay, so now let's compare the communication costs of local and global fanouts. So first, if we look at the global fanout, you see that the time of the global fanout is the total amount of communication, V2, divided by, if we assume a good spread of the communication, the number of nodes, P2, times the cost per data word, G2. And that's a higher cost because it is between nodes. It's not within a node. So on the other hand, the local fanout, we have that's super step 1, we have the total volume V1, which is the total number of data words that are being sent from any core to any other, and they are within the node. And then we divide that by P, because there are P cores that are sending, and the cost is less per data word, it's G1. And, and then you can see the difference between the distributed memory and the shared memory. It is more costly to have a global communication. And looking at the formulas for the global fanout and the local fanout, you see that the cost for the global ones is G2 divided by P2, and the local one is G1 divided by P. So if we call this ratio beta, then this turns out to be G2 divided by G1 times P1. Note that not only do you have the per word costs of communication, G2 divided by G1, but also in this formula we have a P1 which appears because we are modeling P1 cores together as one node. So this is really the cost difference. That's your gain if you run something and you exploit the fact that local communication is cheaper. Okay, how does V grow as a function of the number of processors? If you cut more and more pieces, then obviously the total amount of communication will grow. Here we see what happens for a two-dimensional grid. If you look to the left, we have 4 processors. To the right, we have 16 processors. And if you look at what happens to a square, and then forget just about the boundaries, then the amount of communication doubles. For example, if you have a horizontal boundary, you get an extra horizontal boundary within that part if you split it into 4. So we have that increasing the number of processors by a factor of 4 doubles the amount of communication. That means that V goes as the square root of P, and that's in 2 dimensions. In 3 dimensions, it's like the cube root. So we not only have a matrix distribution, we also have a vector distribution. And in the vector distribution, we have to decide who is the owner of a certain component Vj, but also who are the owners of the local copies. And the matrix distribution minimizes the communication volume. The vector distribution balances the volume. Okay. After the global matrix partitioning, we can determine already the node S that has a certain vector component Vj. So we denote that by 2 parameters, the S, and then the unknown phi v of S of this component J. And then we have the local matrix partitioning, and after that we determine the local owner of the copy. Okay, let's summarize. We have motivation to use the hybrid-BSP model, and that is if we have a large value of beta, if there's a big difference between the communication in distributed memory or in shared memory. And so we have a simple hierarchical model with 2 levels. And if we then write an algorithm, we have both local supersteps within a node and global supersteps that encompass all nodes. Then, if we apply this to our BSP algorithm for sparse matrix vector multiplication, then we get altogether 7 supersteps, which are 4 local ones and 3 global ones. And then we partition the matrix accordingly for the global and then for the local. Now a final question. Assume that you have 1 million numbers that you want to add on a hybrid BSP computer, which has 100 nodes. Each node has 10 cores. And we only need the answer in one processor. How would you do that? Now, if you assume that the computer has the parameters G1 is 10, L1 is 100, and the parameters G2 and L2 are 10 times higher, what would the BSP cost then be of your algorithm?